those of you who are here for my previous lectures know that the first slide always has a riddle. The riddle here, in this slide, there are 3 supernova progenitors. Can you identify them?
Usually there's an arrow.
Right. I told them that in the first lecture, that the easy way to find a supernova progenitor, it's the one that either has a circle around it or an arrow pointing at it. But in the riddle part, we don't have arrows. So, where are the supernova progenitors? Betelgeuse, right. So this is the constellation of Orion. This is Betelgeuse. It's a red supergiant star. It's going to explode as a supernova based on what we know. Okay, that's progenitor number 1. Next. Sirius, right, Danny. How did you know? We have the number 1 expert for type 1a supernova progenitor. So this is Sirius. This star is an A star. Eventually, it's going to evolve into a white dwarf. It has another white dwarf companion, potentially even a tertiary. And those 2 white dwarfs, eventually, in the far distant future, will take many, many Hubble times, but eventually they will lose energy and collide, merge, whatever, and explode as a type 1a supernova or something similar to it. Okay, the third one. I thought this was the difficult one. Okay. You're not a student. It's not fair that you're giving. Okay. This guy, Rigel, is a blue supergiant. It's a very luminous, massive star, and based on what we think, is also going to explode as well. So there are at least 3 supernova progenitors in this image. There could be, right? There could be more. I said 3 that we know about.
For sure, there are more. There are hundreds of supernovae progenitors.
Yes, in the Orion Nebula. That's true. Now, if this was a video, we could have just sat here and waited for the rest of the talk. Maybe something's going to happen. Okay, good. Okay, so you solved the riddle, even though 1 student gave 2 answers. It's not a good practice for the class. Okay, I will forgive you. Okay, so the topic is massive stars and supernova progenitors. My focus will definitely be on supernova progenitors. So we will discuss massive stars as supernova progenitors. It's not a lecture about massive stars for 2 reasons. 1 is that I don't know enough about this, and 2 is that it will require a lot of time to talk about all the aspects of massive stars, which is a very complex field. This is a version of the Hertzsprung-Russell diagram that you already saw in previous lectures. And it includes the relevant populations that we will be discussing as massive stars that are supernova progenitors. In particular, we were discussing red supergiants, so here they are. Red, low temperature, supergiant because they have very high luminosity. They are more luminous than giants. These are blue supergiants. Also, we think those will become eventually supernova progenitors, as well as here the top of the main sequence. These stars will eventually evolve off and explode as a supernova. Type 1a supernovae and maybe some other classes of events might also come from white dwarfs that explode in a thermonuclear explosion, and we will discuss this a little bit. Okay, a few numbers to remember. In terms of radii, when we say something is a supergiant, the typical number for radius to remember is 10 to the 13 centimeters. Of course, there's some range of radii. Some are bigger than others. The sun, who remembers the radius of the sun? 1 solar radius, very good, yes. In some other unit, not in inches. Right. So it's less than 10 to the 11, right? So these are much smaller stars. Wolf-Rayet stars that are evolve off the main sequence are typically small stars of order 10 to the 11 centimeters. Blue supergiants are somewhat smaller than red supergiants. They could be maybe 10 to the 12 centimeters. And white dwarf stars, 10 to the 8 centimeters or so. Okay, much smaller. Okay, so this is as far as radii are concerned, and luminosities. So here, the really most massive stars are about 1,000,000 solar luminosities. Here I don't need to use any other unit. So 10 to the 6, 10 to the 5, this is supergiants, and then there are stars all the way down. Okay, good. In terms of supernova progenitor detections, if you just stop to think about this, studying supernova progenitors is a difficult question because typically you know about the object you would have liked to study once it's exploded. So intrinsically, it's a difficult question because the perpetrator already destroyed all the evidence once you know about the crime. So how do we do this anyway? So there are a few methods. I listed them here. It's not exhaustive. There are a few other approaches that are also, of course, usable. But these are, let's say, the main ones. The first one, which is maybe the most straightforward and broadly used, is called direct imaging or pre-explosion. And this is a picture we already looked at the previous lecture. So this is which supernova? 87A in the Magellanic Cloud. And this arrow is pointing to the progenitor, which was this particular star. And because people studied this stellar field for many decades before the supernova explosion, this star was well documented, it was cataloged, there were measurements of it, there was even a spectrum. So we knew a lot about the star because we studied it before it became a supernova. Now, of course, you have to be lucky for that to happen in any random galaxies because most stars in nearby galaxies that we can actually detect individually are not studied anywhere close to the level of study of this particular star. But if you have pre-explosion imaging of the location of the supernova, you can know something about the progenitors because it just happened to take this data, usually for some other purpose. I say it's the most informative method because the number of assumptions that you have to assume to translate your observations into knowledge about the physical status of the star is the minimal, right? Remember that the thing that we measure from this picture at most is the luminosity of the star. We want to translate it to some physical things like mass, radius, and so on. So there are assumptions that go into these translations, but they are minimal. In other methods, we need to make much stronger assumptions. The problem with this method is that the progress is very slow because the number of supernovae that explode in the nearby universe where we can resolve individual stars in nearby galaxies using our current equipment is small. So every year there's 1, 2 events like that where they explode in the nearby universe. We happen to have pre-explosion imaging usually from the Hubble Space Telescope, and it used to be people rush around and study these images. Now it's more relaxed because it's been done many, many times. So people go locate where the supernova happened in the pre-explosion image, see if there's a star there, and if there is a star there, what sort of star was it? Now let me make an important point that was recognized more strongly in recent years. To really be convinced that something is the progenitor of a supernova, it's not enough to show that it was at the location of the supernova. So let me show you. So this is a supernova, and this is a pre-explosion image of the same field from the Hubble Space Telescope. You identify the center of light of the supernova, you project it to the previous image, there's some astrometric error, and you identify an object here. This is not good enough to say this was the supernova progenitor because there could be chance coincidences, there could be another star inside your uncertainty region that has not exploded. If you have an image taken a long time or long enough time after the supernova happened, where the supernova is decayed, and you go back and you see that the star really is gone, then you know this was the right star. And this is what we did here, okay? So you can compare this panel with that panel, and you see that all of these sources remain, and this one is gone, so it really exploded. Now this requires patience, because it means that from the time the supernova happened until the time you can be sure that the object you are studying is the real progenitor, it takes a few more years for the supernova light to go away. You would have thought, well, how commonly it happens that you get the wrong progenitor? And the answer is it's very common. It's about 50% of the time. So initially, it was indeed, people said, well, okay, there's a star over there. It must be the right star. And it turns out that half of the times, it wasn't the right star. Now, also, another final thing to note, if you read the literature, in principle, whenever you do this exercise, you calculate something you call the chance coincidence. What are the chances that a star just happened to see it where the supernova went off? And typically, many papers, this is done by using the same data itself. If you take this as an example, you say, okay, I have this square. There are so many pixels here. How many stars as bright as the supernova progenitor are here? Maybe a few. I will divide the numbers of the stars by the number of the pixels, and I get the chance that some pixel will have a star like that. This is totally wrong for massive stars. It's very wrong. Why is it wrong? Because that takes more than one pixel. That's okay. Let's say we corrected for this effect. It's true, of course. It could depend on the band, but it's more deep. It's deeper than that. That could be true, but I think that when you do this thing, you assume that there is a uniform distribution of stars, that the probability to find a star in a pixel is uniform across your field of view. We know for certain that this is very wrong for massive stars. Massive stars are intrinsically clustered. If you tell me where there's a massive star, the chance to have another massive star right next to it are much larger than anywhere in the volume of the universe, or of the galaxy, or of the same area of the galaxy. Right? They are clustered. There's strong correlation between having one massive star to having another massive star. So, for example, if you look, at least half, usually more than massive stars are in clusters or associations. So they are next to each other in space.
You're not talking about binaries, something more.
No, not binaries. There are, of course, binaries, but even if we disregard binaries for a second, the closest neighbors in terms of massive stars to massive stars are other massive stars, right? So they are clustered together. And you have to take this into account. And to really properly take this into account, you have to know the clustering properties of massive stars in the location of the supernova, which is something that you usually don't know. Or if you really want to do it properly, you should measure. And so doing this thing of saying how many objects as bright as this one are in the picture and what the chances of one of them falling on this pixel is wrong. And this is why initially you got all these wrong identifications. Because if you are looking at a place where there are many, let's say, red supergiants next to each other, and one of them exploded, we know it was there because the supernova came from it, the chances of having another red supergiant very close to it are very much larger than just having a red supergiant somewhere in the universe. Right? Okay. So this is something you have to keep in mind, and you have to keep in mind whenever you do a chance coincidence test. Right? If you're assuming uniform density of the sources you're studying, is this assumption correct? Often, it's not.
Are you talking about windows that you can't resolve? Like you're looking at some area, some pixel
Yes.
range that you can't...
Yes.
So that's something that you could, at the post-explosion, like very much after the supernova decay, you could look at it and see...
Right. In fact, this is a good example, right? You see, there's something here. That's probably another massive star. Right, you can argue whether it is inside or outside of this arrow region, but there's another massive star right next to the one that exploded. This is not surprising, because it's probably related to it in some sort of structure. Or I'm not saying it's a binary companion, it's probably not, because every pixel here is many parsecs, but it's probably related to the same group of massive stars. Right? So a supernova went off, we know there was a massive star there, the chances to have another massive star right next to it, unrelated, physically unrelated, or at least, gravitational bound maybe in a big structure, but not a binary companion, just a random chance coincidence, very high, very much higher than just saying what the chances are for any massive star. Okay, this is taken already too long. Next, okay. Another method, which I will talk a little bit about, is quite a big range of what we call environmental studies, which is a supernova went off. I don't know what was the progenitor, but I can look what is around the progenitor and say, does this tell me something? And for example, because of what we just said, massive stars tend to be born in areas of active star formation, where you have all kinds of tracers for that, like other massive stars, or H2 regions, which are a concentration of gas. And you can say the distance between the supernova location and the nearest concentration of star formation should be shorter the more massive the progenitor is. Because it's short-lived, it couldn't have moved away far from where it was born, and where it was born, there would be a lot of star formation and other neighbors there. And this is an example, we look at them later on from a recent paper, where you see that the distance, we'll talk about these particular diagrams, but what it shows is that different supernovae have different statistics of distances from tracers of star formation, and that could tell you something about the nature of the progenitors in a statistical sense. So this does not tell you about what the progenitor of a particular supernova was, but of a class of supernova. And there are other aspects like that. The third sort of a method that is now becoming more and more useful is studying the early emission from the supernova. The early emission of the supernova, we'll discuss this towards the end of this talk, encodes a lot of parameters of the progenitor. The easiest, perhaps the easiest to explain, and I will just say this briefly, when the supernova explodes, you deposit some energy into a ball of gas, which is now going to be the expanding ejecta of the supernova. And this expansion is very rapid. It will double its size in an hour and continue doubling again and again. So it's cooling, there's a diabatic cooling which is very strong. The amount of a diabatic cooling depends strongly on the size of the original progenitor. If the progenitor was very small, maybe 10 to the 11, it's going to double in size during the first few days many more times than if it started at 10 to the 13. So it's much easier to keep the ejecta from a big star hot or warm than from a small star. A small star would cool very rapidly. Type 1a supernovae, for example, if you start from 10 to the 8, the explosion energy is cooled so rapidly that it's almost impossible to hope to observe it there. It expands to, 10 to the 13 centimeters in a couple of hours. So all of the explosion energy is immediately, it goes to, if it didn't have any radioactivity, it would go to 0 degrees. Okay, good. Okay, now we stopped with methodology. We'll return to this again and again during the talk. Let's start talking about supernovae, and even though the lecture is about massive stars, I will start with supernovae from low mass stars, just to be complete. And the most common and well-studied events from low mass stars are type 1a supernova explosions, and maybe the best direct evidence for that was recently obtained by Nugent and collaborators, and then several follow-up papers from observations of the very nearby type 1a supernova, 2011 FE in M101. And the methodology here relies on early observations of the explosion. And what you see here, these red curves show you the emission you should have expected from an explosion of a type 1a supernova with the standard energy as a function of the size of the progenitor. So this is 100 solar radii, 1 solar radius, 0.1 solar radius. And this is the observation. So you see that the fact that we have so little flux shortly after explosion means that you cannot have large stars, not even 1 solar radius. And this is direct evidence that the star was much smaller than the sun, and if it was much smaller than the sun, it must have been a white dwarf. Now you could say, well, we knew it was a white dwarf before, but this is direct evidence rather than based on all kinds of complex analysis of the spectra and light curves and so on, which are, of course, also consistent with that. One point I wanted to make about progenitor of type 1a supernova, we cannot go in depth into that, is that there are two, let's say, big classes of models. These white dwarfs are in principle stable. Why should they explode? Well, they are in binary systems. And then one class of models has a white dwarf with some other star that is not a white dwarf, and then maybe there's accretion from the big star to the white dwarf and so on. The mass grows up. Eventually, it will explode. These are called single degenerate models. So there's only one degenerate star, the white dwarf that is about to explode. And the other one has another white dwarf colliding or merging or somehow joining with the second white dwarfs, and these two white dwarfs explode together. These are called double degenerate models. There are many submodels of both types. In my brief view of that, I would say that single degenerate models are disfavored for the majority of the objects, mainly because, in my personal view, there are other claims. It all points in the same direction, but the main thing is that the single degenerate model is a predictive model. There are many predictions for things that you could have seen if all type 1a supernovae are single degenerates, And all of these things that you could have seen, you don't see. And this includes, for example, there will be a talk about this interaction with this companion, right? You have non-degenerate companion donating mass to the white dwarf. You should have seen this interaction sometimes. You don't. In supernova remnants that came from type 1As, there should have been the surviving mass donor in the center. You search for it, you don't find it. This mass that you get to the type 1A supernova should contain a lot of hydrogen. You look for this hydrogen, you don't see it. All of these things you could have seen and you don't see in many different experiments. So overall, I think most type 1A supernovae, or at least the ones that we call normal, don't come from single degenerate systems. They must come from some sort or other of the double degenerate variants. There is one puzzling observation that is still sort of suggestive of single degenerate models, and this is one example of a study like that, which is when you observe at high resolution, you observe type 1A supernovae, often you see absorption features from gas in the vicinity of the explosion, and more often than not, these seem to be blue shifted with respect to the supernova. Right? So you're seeing some sort of low velocity outflow from the location of the supernova. This is based on statistics that Sternberg et al. Published a few years ago, and they show that in type 1A supernovae, the majority show blue shifted emission, the minority show red shifted emission. If this were random clouds of gas in the galaxy, it should be equally likely. And you see that indeed, for example, if you look at random fields of view, lines of view in the Milky Way, it is indeed blue shifted, red shifted, and no absorption is more or less equal. Absorption. This is some gas that is in between us and the supernova. But the fact that we are seem to be seeing, and this has been since then confirmed in other studies, seem to see more gas outflowing from the supernova location than towards the supernova location, seem to suggest there's some sort of outflow. And in principle, at least in the naive models of binary white dwarf systems, they shouldn't have any outflows. So this is a puzzle. Either it is unrelated to the supernova, or if you want most supernovae to come from binary mergers, then you have to somehow explain this observation. Okay.
Are these lines narrow or
Narrow. Often you see many components. Each component is very narrow. It could be, a few kilometers per second. And the distribution of velocities, let's say, you can have several blue-shifted components, and they span maybe 150 kilometers per second and so on. So these are low velocities. They are not... certainly, you could have these coming off as winds or something from some system. Right. Typically, quite often, you see many absorption features at different velocities, all of them blue shifted, and the range of velocities would be from 0 to, let's say, 150 kilometers per second. Yes.
What is this Milky Way supernova category?
This is if you use supernovae outside of the Milky Way and look at the gas in the Milky Way and ask whether it is moving away from us or towards us. So you're doing the test on the Milky Way as a proxy for the supernova host galaxy. So you can do it with supernovae outside of the Milky Way or with quasars. And core collapse supernovae that come from massive stars, there you expect to have outflows because this happen next to stars with winds and cluster and stuff. And even there, the frequency of outflows is not as large as in type 1As. Okay. This is, if you're interested, there's quite a bit of literature on that. You can go read. Okay. Now let's talk about peculiar type 1A supernovae. Unlike the majority of type 1A supernovae, where I think there's no strong evidence for single degenerate models, there are some indications for single degenerate progenitors, so a white dwarf accreting material from a secondary that is not a white dwarf, in some peculiar type 1A supernovae. There are now two, I think, more convincing claims to see a UV brightening at the early phases of a type 1A supernova that could be interaction with a companion. This is by Zhao et al. You can see here, this is the UV light curve. So you see initially there's a flare, you see decline, and then the supernova goes off. And this is compared to measurements of many other type 1A supernovae that none of them show this phenomena. And this is more recent from a paper by Griffin, here, who's sitting here, also showing this UV bump here. So you can hear more about this. I think Dan has either given or will give you a lecture about this in particular. Both of these supernovae belong to some peculiar subclasses of type 1a supernovae. And then there's quite a number of studies on this particular class of peculiar type 1a supernovae that sometimes people call 1ax. We mentioned in my previous talk. In particular, there are these two studies based on HST imaging. McCulley et al. Detected a potential supernova progenitor. This is this blue star here. You see it's right where the supernova went off. It has a visible light magnitude, absolute magnitude of minus 5.3. That's a very luminous blue star. Technically, it's a supergiant, right? Not what you expect for type 1a supernova, but if you read a paper by McCulley et al., they make the case that it may have been a white dwarf accreting material and becoming very luminous just before it exploded, or at least partially exploded. This is one case.
Do we know by now if it's gone away?
I asked for updates about this from McCulley and Ja and their collaborators, and there's no recent update. I know they have been trying to follow the supernova and wait for it to become faint enough so they can re-image with HST, but apparently they either don't have the data yet or unwilling to tell me what the result is. But I think it's the first one, actually. If somebody in the audience knows more, then they can say. The second thing, again, another member of the same class, there's a paper by Foley et al. Who looked post-explosion and found a red source at the location of the supernova. And this source is quite luminous. It has an infrared luminosity or I band minus 5.4. Again, technically, this makes this a red supergiant. Now, and you see that there are many other sources like this in this area. Now, whether this is related to the supernova or not is still an open issue. And again, probably the thing to do is to wait some years and then get more information, more observations from Hubble and see if it goes away or goes up or remains steady. If it's steady, it's probably unrelated. If it's somehow the remnant of the explosion or the mass donor or something, then you might hope to see some change. Excuse me? Yes. So they were following up after the explosion and found this. The supernova is gone, but there's this red remnant over there. There's no pre-explosion image for that particular supernova. Yeah, the galaxy is a star-forming dwarf galaxy that was not well studied before the event happened there. Now, one thing, of course, to note is that it so happens that, at least for this one particular class, both events happen to fall on the location of a supergiant. So if I didn't tell you anything else, you would have said these are co-collapse supernovae. So in principle, you might even think that maybe this subclass of type 1a supernovae actually is contaminated by some explosion of massive stars that just look like type 1a supernovae. That's something to keep in mind. Finally, the final thing about type 1a supernovae is that I already showed you this before, but there is a class of type 1a supernovae that initially look like regular type 1a supernovae and then start interacting very strongly with circumstellar material, many solar masses of hydrogen, or what seems like many solar masses of hydrogen. And this is the most convincing one, maybe PTF11KX, that initially really looks like a type 1a. You already see this emission and absorption signature of circumstellar material, and later on it becomes totally dominated by interaction. Unless there is some very strange coincidence, if this material had to come from the progenitor system, it must be a single degenerate. This is a very rare class of events, but at least those guys could be some sort of single degenerate systems, and there are specific models how to make this. For example, if a white dwarf merges with the core of a giant star, let's say, or something like that. Okay. The last class of supernovae I wanted to talk about that are, in my opinion, unrelated to massive stars and are not type 1a's, are what we call the calcium-rich supernovae that are technically, at least most of them are type 1b because they show helium. And the main point I wanted to make is that the location where these transients happen suggests that they must come from old stellar population. First of all, they happen in the remote outskirts of galaxies, which is itself very puzzling. And this is just plotting the fraction of these events. These are these events in red as a function of the galaxy type, where here we have star-forming galaxies And here we have passive galaxies with very little star formation. And you see that the core collapse supernovae typically are more and more abundant as we go to star-forming galaxies. Type 1a supernovae occur in passive galaxies and also follow this curve. This is the subclass of normal type 1a supernovae that is preferentially. It's a cumulative, right? Yeah. No, I'm not saying that there is also where you put the differentiation in here doesn't mean, but it means that the distribution is skewed. No, but I'm saying that these guys, the distribution is skewed towards these early types of galaxies, right? There are more of them here than here. When compared to this, right? If you take this as a baseline.
Curve rises more steeply.
Right.
Final value.
Exactly. Right. This is not to say there is something about the rates or anything like that, right? So these are calcium-rich events, and they are more concentrated in early type galaxies than regular type 1as. So I think, if anything, they come from an older population than type 1a supernovae, which themselves come from white dwarfs, which are not massive stars. Okay, this is quite a bit of puzzle. There's a bit of puzzle about these calcium-rich events. Okay, now let's return to massive stars, and so let's look again on the HR diagram, but now it's less nice to look at, but it contains more information. So to orient you, so this is the main sequence. Here we have these red supergiants we discussed before, blue supergiants. This is the top of the main sequence. And I wanted to point out a few groups of stars. These are the red supergiants. Here's Betelgeuse we discussed before. Here's Rigel, the blue supergiant we talked about. This is stars in our galaxy. It's the entire galaxy based, all the massive stars. I'm not sure that all of them are placed on this, but many of them. And now we are talking just on the top, right? The white dwarfs and all the other stuff, the faint stuff is below. This is the sun, and all of these stars are more luminous than the sun. This is in absolute magnitude, so each step like this is a factor of 100, right? So this is 100 times and 10,000 times brighter than the sun. Here at the top, there's a group of luminous blue variable stars, LBVs, and these include the most luminous stars in our galaxy, including, for example, this very famous star, Eta Carina, and other stars. This is 10,000. This is 100,000. Sorry, no, this is million.
3 times.
Right. Yes, sorry. Yes, 100, 10 to the 4, 10 to the 6. Correct. Thank you. Yes, million times. Here you have what people are calling yellow hypergiants. These are supergiants. These are brighter, so they are hypergiants. And they call them yellow because they have the same color of the sun. So it actually makes sense. So we have some very luminous stars here in the middle. These are Cepheid variables, so we will not talk about this, but these are very important stars to measure distances. Here's Polaris, the pole star. This is a division, some division that stellar astronomers use to define stars according to their luminosity. So type 1 are supergiants, 2 is what they call bright giants, 3 is giants, 4 is subgiants, and 5 is, which include these stars, are what they call dwarfs, which are basically main sequence stars. So, and then there you see there's 1A0, 1A, 1B, okay. But basically, all of these are supergiants. These are the giants, and these are main sequence stars. Okay. If you ever look at a star, they could say it's an M1A, so that means it's a 1A supergiant from spectral class M, which means it's a cool star. Okay, so right. So this is a more detailed map of massive stars. So we identified several stars that will become important: the red supergiants, blue supergiants, luminous blue variables, yellow hypergiants, and here at the very blue end there are Wolf-Rayet stars, which are like very hot supergiants. Okay. Now let's just review what we know about the progenitors of supernovae by type. now we are talking about supernovae that come from massive stars. And we begin with the most common type, which is the regular type 2 supernovae. And here is maybe the most spectacular example of a detection of a progenitor of a supernova. It's even nicer than 87A. You can see this area with many massive stars in a galaxy. And then the supernova went off. And then when you come back to it, a red star in this location disappeared. So this is very convincing, right? The progenitor of this particular supernova was a red supergiant. There's no argument about that. It very well demonstrates the fact that this is a dense area, right? So below or hiding next to the red supergiant, there's another blue star, and there's another one here. And actually, if you didn't have the other image, you might have thought that the progenitor was this blue star, even though it's unrelated, obviously, because it stayed there. And this is quite typical. Among type 2 supernovae, if you remember my previous lecture, there's a big fraction that remain constant in visible light over the 100 days after explosion. These are called type 2 plateau supernovae. And those plateau supernovae typically have red supergiant progenitors. And I try to be very careful in the way I quantified it in these statements. All the ones that have progenitors that we have identified are red supergiants. There's no supernova like that where we have proof that it is not a red supergiant. But there is a fraction of them for which we don't know the progenitor. And in principle, for some fraction of those supernovae, it might not be a red supergiant. So there's still this uncertainty, but everything else points towards red supergiants. Yes?
How many is several?
Several, with this level of certainty, less than 10. Yes. This is after like decades of work. So you see that the numbers are not going to grow significantly. There is a similar number of objects for which we don't have this part, but we do have this part, right? So there is a red supergiant there, but we still haven't confirmed it's there.
Avishai, you can make a stronger statement, right? Based on these numbers. So 10 cases you could have had good information, and in that case you always found a red supergiant.
No. The 10 cases are ones that I saw a red supergiant progenitor, less than 10, and it disappeared later on.
Right.
So this is confirmed. There are maybe similar number of events where there is something that looks like a red supergiant, and we don't know if it disappeared or not because we haven't looked yet. And there are yet another number of events where you looked and you don't see a red supergiant, but because of the quality of observation, there could still be a red supergiant there, but you don't see it. Maybe it's a bit less luminous or so on.
Based on that, you can say what fraction of the type 2 beats are definitely
Red supergiants?
yeah,
Yeah, I think, I don't know exactly, but I think 50% is a good estimate. Yeah, maybe it's a bit more, a bit less. At least, yes. And yes, and they say, do you have a proof that no, it's not 100%? No, it could be 100%, and it's probably at least 50%, something like that. Now, if you read the literature, there's a quite famous claim by Smart, originally from 2009, of something it's called the Red Supergiant Problem. And it's actually a very interesting observation, which is if you look at the luminosities of those red supergiant progenitors that you identified, and you translate to the best of your ability this luminosity into a mass, the masses of these red supergiants are between 8 and 16 or 17 solar masses, with some errors on the top. It may be, some of them are maybe, we thought they're 17, but maybe they are 19 or 20, but that's it. So this is the range of masses that we see. Now, if you look in our galaxy, and you just list all the red supergiants that you know, and you take their luminosities and translate them to mass, the distribution of red supergiant masses extends certainly above 20 solar mass and probably up to 30 solar mass. So there's a population of red supergiants that exist in our galaxy, but seem to never explode as type 2 supernovae. And if you say, well, maybe you're missing them, those are the brightest supergiants. So those are the easiest one to see. So if we're missing somebody, it shouldn't be those. It should be the ones that are faint and low mass. So it's hard to think this is just observational bias. And this is called the red supergiant problem, or the missing red supergiants. And the idea is, what happens to these massive red supergiants? They must explode. They don't make supernova because we never see that. So what happens? And then Smart, I think quite strongly in this paper from 2015, argues that they are failed supernovae. So the stars exist, and they undergo core collapse, but they don't explode as luminous supernovae. And if you remember previous talks, there are certainly models of supernova, core collapse supernova explosions that predict that there would be a big population of events that go to black holes, and maybe these black hole events do not end up in supernovae, but rather in direct collapse to a black hole or almost direct collapse that doesn't make a luminous transient. Other people, there are quite a few of them, disagree, not quite a few, but several of them disagree with this statement on various grounds, and I think the most recent one, and which is also quite convincing, is by Davis and Bezor. And they actually say there's nothing wrong with your argumentation about supernovae, but if you look at red supergiants in our galaxy and see how they age, how they develop with age, you see that the more evolved they are, so closer to becoming a supernova, they become a bit cooler. This means that the luminosity is more or less the same, but it goes in redder and redder bands, which makes them look less luminous if you are observing in an optical band, which is almost all of these observations. So what they claim is that if you take a pre-explosion image of the supernova where the red supergiant is very old, it's about to explode, it might be much cooler for the same luminosity than its analog in our galaxy, which could be 100,000 years from exploding. And there, since you don't measure the bolometric luminosity, but just the luminosity in optical light, you are underestimating its mass. And they claim this can actually solve this entire problem. And whether or not it's true, you actually have to be an expert in red supergiants to understand them. The best expert in red supergiant that I know is this guy. So, but I'm not saying this necessarily is correct, but it's certainly a claim to be held. Was the question? Yes. So there's one case like that. I actually had it in a slide in the first lecture. I don't have a slide in this particular presentation, but since you asked, let me say a few words about that. So there's a group out of Ohio State that for about a decade are taking deep images of nearby galaxies and monitoring the stars in those galaxies, looking exactly for that, for a star that would be there and then disappear without a supernova. Sometimes they call it a survey about nothing, or they have all kinds of cute names for this survey. And they have one very interesting observational case where they actually see a red supergiant, and then it sort of disappears. I will explain what sort of is. And they actually searched in archival PTF data, and they found that around the time it disappears, there's a small flare that PTF detected but did not trigger on because it's very low luminosity. So it seemed like there was some sort of blip, and then the star changed dramatically. It disappeared from the optical. It's still visible in the infrared. And the question now, is it reasonable to think that a failed supernova will still remain visible in the infrared for several years after the collapse, due to the fact that it takes time for all the envelope to actually fall onto the remnant or dissipate somehow? And they claim that it's at least possible, and yeah, so this is something I think is not well studied, but this is the most intriguing case, at least I know of, for this thing. And certainly this survey or other surveys like that should detect this population of disappearing stars if they are common.
And could they estimate the mass of the phenomenon?
I don't remember exactly the mass, but it's of order 10. I don't remember exactly the details of this particular, but certainly, no, it must be more than 10 to be a failed. I don't remember. It's probably in that paper. It's a good question. Adams et al. This is the reference. Okay, good. So this is what I had to say about regular type 2 supernovae. A subclass of spectroscopically regular type 2 supernova, even though many people would not say they are regular in any ways, supernova 1987A and many of its companions, or not companions, but events with similar properties. Now, the supernova 87A had a blue supergiant progenitor. I wasn't there at the time, but people tell me this was a huge surprise, and many people were amazed by this observation because they expected type 2 supernovae to come from red supergiants. Anyway, it definitely had a blue supergiant. You couldn't argue about that. And eventually the theory actually explained how some massive stars, low metallicities in some mass ranges, become red supergiants and then become blue supergiants and red supergiants again. This is called the blue loop. They can undergo one or several of these blue loops and explode somewhere on the loop, including on the blue side. So we know that there are events that come from blue supergiants. There are compilations of similar events that the latest and most comprehensive one I show here is Tadia et al. 2016. And there has been some modeling, and they claim that all or most of these also come from blue supergiants. One thing I wanted to point out is that some of these events that are similar to 87A, and I remind you that what defined 87A, this, you can see this based here, most here, is that it doesn't have a plateau. It has a very long rise that can extend to 80 or more days. So it's rising very slowly and then coming down, and then it becomes similar to regular type 2s. So some of those events, at least initially, have quite extended plateaus. And they only then develop this big bump that you see in 87A. So at least some stars in nature seem to be blue supergiants, but also know how to make some sort of plateau. I don't know exactly what it tells us. But what I'm saying, for me personally, it's not clear to me that a minority of type 2 supernovae, even type 2s, or at least type 2, some type 2Ps, or some with strange type 2Ps might come from blue supergiants. Not all of them necessarily are red supergiants. Maybe they are, but I'm not sure. Okay, so that ends what I had to say about spectroscopically normal type 2s. Now let's talk about those that are not spectroscopically normal. One class we discussed was type 2b supernovae. These are supernovae that develop very strong lines of helium. So initially they are dominated by hydrogen, but then they evolve to have more helium lines. And in that respect, they are similar to type 1b supernovae that are very helium rich. And now there are several of those events that happen in nearby galaxies for which we see two interesting things. One is that they come from supergiants, but these are not red supergiants, but rather yellow or orange supergiants, so they are hotter than the regular red supergiants, if you remember the picture I showed you before. And the second, that there is quite a bit of evidence that these events come from binary systems, and in particular, these hypergiants seem to have blue binary companions that are also massive stars. And this is a beautiful observation from Mound and Smart 2004. And what you see here, this is a spectrum of the supernova at late time. And then this is a zoom of this area of the spectrum. And you see there are these absorption features in the spectrum. And here they compare it with the spectrum of a B supergiant. So this is a blue supergiant, and you see that these features align. And here they even scale the spectrum and plot them together. And you see that apparently this spectrum actually contains light from the supernova and additional light from a blue supergiant star, which of course they suggest is the companion to the progenitor that survived. And there have been attempts to further confirm this and get actual spectroscopy of the star, but this has so far mainly failed. Okay. So I think certainly there's a, let's say, notion in the community that type 2b supernovae, probably at least many of them, come from binary systems, where the one that is about to explode is a yellow or orange supergiant. The typical masses of these binary systems are initially something like, say, the models that are published are, like, say, we begin with 14 and 15 solar mass stars. The 15 solar mass stars start to evolve early on, transmit some mass to the secondary, and then eventually explodes as a hypergiant with final mass of, I don't know, let's say 8 or something. And the rest of the mass went to the secondary, so the secondary would now be 20-something solar masses and a very luminous blue star, which is also going to be a supernova progenitor in the next generation. Yes, this is one. I'm not saying this is true for all of it. This is one model that is in the literature. Another observation on type 2b supernovae is based on observations of very early spectra of a type 2b supernova, this particular one, 2013 CU. And here I am comparing the spectrum of the supernova during the first night after it exploded with model spectra and with real spectra of Wolf-Rayet stars. Wolf-Rayet stars are very luminous blue stars that have winds And from these winds, you see emission lines. So unlike most stars where you see mostly absorption lines, from these you see mostly emission lines. And you see that the same emission lines appear in the spectrum of the supernova and of these stars, not only the same lines, but even similar profiles. And from that, you could say that the progenitor had a Wolf-Rayet-like wind. It doesn't mean the star necessarily was a Wolf-Rayet star when it exploded. In fact, there is some evidence that it was larger. Right? You remember, at least for other type 2b supernovae, the progenitors we observed were supergiants. But the composition of the wind, at least, was similar to those of Wolf-Rayet stars, which means it was hydrogen poor and enriched in helium and CNO processed material. So this is something that tells us about the composition of this progenitor, and this technique of getting very early spectra is going to become, I think, quite important in studies of supernova progenitors in the next few years. The next subtype I wanted to discuss was type 2n supernovae. So these are supernovae that when we observe them even early on and also later, they show strong emission lines of hydrogen. And here, for some events, and I already showed you this figure, we see direct evidence that some of these events come from very massive stars with very high mass loss rates. So the circumstellar material that the supernova is interacting with is massive, and it comes from the star itself. And this is actually the figure I already showed you. This particular star here exploded, disappeared. The luminosity of this star is about million solar luminosities. Okay, so million solar luminosities, if you remember the HR diagram we looked at before, it's really at the top. It's similar to the most luminous stars in our galaxies, which are all LBVs. So this certainly is consistent with this idea. And all kinds of other lines of evidence suggest that there was something like an LBV before the supernova exploded, because something had to place this massive CSM around the star, and we know LBV stars do that. However, and I listed here a bunch of other papers. However, if you do population studies of type 2n supernovae and ask, as a population, are they located in the places you would expect to find the most massive stars, like the LBVs in our galaxy? The answer is definitely not. In fact, from all core collapse supernovae, they seem to fall in the locations least associated with star formation rate, less even than regular type 2s, or at least similar to that. To me, this suggests that probably because what we define type 2n is based on the signatures of interaction, we are probably mixing some populations together. We are mixing a population of very massive stars that emit some CSM and then interact with it when they explode, with maybe other less massive stars that somehow also lose some mass and interact with it when they explode. Or maybe we then don't explode, and if you remember Stell's talk, if you have, let's say, a common envelope merger, a common envelope and then a merger of two stars, during the common envelope, you can deposit a lot of mass in the vicinity of this system, and then the merger itself can provide something that will interact with this CSM to create something that looks like a supernova. This is very interesting and open question. So how to analyze type 2n supernovae? Are they all the same or different? There are different subclasses. It seems like there are, to me at least. Okay, this is the last thing I wanted to say about type 2s. And now we go to the hydrogen poor events. The first ones are type 1b supernovae. So these are events that have no hydrogen or little hydrogen, but a lot of helium. There's only one of them where there is a detection, a direct detection of the progenitor star before it exploded. There's been some arguments about this, about the detection and about which star it is, but this is from the latest paper by Eldridge and Mond. And here is the star, and here it's gone, and this is subtraction of those two images, and you see the residual. So there was a star there, and it's no longer there. And these authors claim it was what they call a helium giant, which means in terms of luminosity, it was a giant, but the composition, unlike red giants that have a large hydrogen envelopes, this one was composed of helium. Now, these helium giants come out of stellar evolution models, but we don't observe them in our galaxy at least. There are not many, or I'm not sure there is even one helium giant similar to this star. But maybe if it's a brief phase of stellar evolution and they don't exist for a lot of time before they explode, maybe we are missing some of them, or maybe there's some observational bias that is prohibiting their detection. Anyway, they claim that it's a 10 to 12 solar mass helium giant, and they also claim that it probably had a companion which is about 10 solar mass or a little bit fainter, and that if we wait even longer, eventually we might be able to detect the companion using the Hubble Space Telescope. Another line of evidence we have about type 1b supernovae is observation of the shock breakout signal from the supernova 2008D. If you remember the talk about X-ray transients, this is the supernova that happened to explode when Swift was observing another supernova in the same galaxy. So we saw the process of explosion, the shock breakout from the star in great detail. And in particular, there are many works on this, but it seems like the observations are consistent with something like a Wolf-Rayet star, so a compact star, maybe with a little bit of gas around it, either circumstellar or some sort of low mass extended envelope. This is from Ganot et al. Comparing the observations from Swift with some Wolf-Rayet models with different compositions. Okay, so early observations here again tell us that something about the progenitors of type 1b. Note that this is different, right? Here they are talking about a Wolf-Rayet star. There we're talking about helium giant. Yes?
What is the distinction between a helium giant and Wolf-Rayet?
Right, so a helium giant, first of all, as an observer, I don't know because I've never observed a helium giant. It's something that exists in books. But Wolf-Rayet stars we know. Wolf-Rayet stars are massive stars. Typically, their masses extend from, I don't know, a few solar masses to tens of solar masses. And they're very hot. Because of the strong radiation pressure, they blow very massive, reasonably massive winds. This material flung from the star is then ionized by the hot surface, recombines, there are emission lines, and I showed you a spectrum before. These are Wolf-Rayet stars. They come in different flavors based on the emission lines you see in the spectrum. There are what we call WN stars that are more hydrogen and helium rich, and there are WC stars that are more carbon rich, and there are WO stars that are more oxygen rich. And again, probably this tells us something about how stripped the original star was. Okay, these are Wolf-Rayet stars. A helium giant is supposed to be a star with a helium envelope and the size of a giant. So let's say 10 to the 3, 10 to the 4 solar luminosities. Now, will it have a wind? Will it be similar to a Wolf-Rayet star or not? I don't know. But its mass is going to be less than a typical Wolf-Rayet star, so maybe 10 solar mass or so. Yeah, that's what I can say. Yes, we'll discuss something about this in a second. Okay, so that's type 1b supernovae. If I want to reflect what the community thinks about this, initially it was thought that these all come from Wolf-Rayet stars, so stars more massive than the progenitors of type 2 supernovae. More recently, many people argued that they actually come from binaries, and therefore they are in the same mass range, but they lost their outer envelope in interaction. This is why we don't see hydrogen, rather than losing it due to winds, as you see in high-mass Wolf-Rayet stars. So this is the big discussion right now, where there are probably, it's probably guaranteed that some of them are in binaries, because we saw that most stars massive stars are in binaries. But whether the dominant population or all of them are in binaries or some of them come from single Wolf-Rayet stars is still, there is still some debate about that.
Maybe we can note about, we're talking about masses of stars.
Right.
And stars as progenitors.
Right.
We should just note that there is a big difference, especially for instance in Wolf-Rayet,
right,
between the initial mass that
yes,
the star was born with and
the final mass.
Before it
right, you're right.
explodes.
Okay, let me talk about this. Thank you. It's a very important point. Right, so Stel talked about this. When stars evolve, they lose some of their mass. And this sum might be a small fraction or a big fraction. So massive stars, in principle, at least the most massive ones, can lose the majority of their mass during their evolution. So a star could begin with 60 solar mass and end up exploding as 10 solar mass star. Or this will be mostly the core material of the star, so the high mass elements. Right? So it can lose a big fraction of its mass and certainly all of its outer envelope during its evolution. So when we discuss the initial mass of the star, which tells us how young it is and how quickly it's going to evolve, And the final mass, which is related to the properties of the supernova, because this is the amount of mass that is available to be supernova ejecta, these could be quite different numbers. For red supergiants, the difference usually is assumed to be quite small. So if you start with an 8 solar mass star, it might end up as a 7.8 solar mass red supergiant. So you lose only a small fraction, relatively small fraction of the mass. Certainly it's true for the sun, right? During the last 5 gigayears, it didn't lose a lot of mass. For some extremely massive stars, you can lose. Eta Carina, for example, it's a very famous example. During its eruption, non-terminal eruption in about 150 years ago, it lost tens of solar masses of its mass in this big eruption, and they are lying around the star right now. The star is probably still plenty massive, so it's not a low mass star even after losing, 20 solar mass to the environment. Okay, type 1c supernovae are ones that don't show either hydrogen or helium, and we assume that they managed to somehow lose all of that envelope material. No hydrogen, no helium. There are no direct progenitor detections for type 1c supernovae, but there are many studies that suggest that certainly they come from massive stars, but also, again, the consensus, I think, is still that they come from somewhat higher mass progenitors than type 2 supernovae, and maybe type 1b supernovae. This is one such study by Mond and Ramirez-Ruiz from last year. This supernova went off in the middle of a cluster of stars, and they actually measured the properties of the stars in the cluster, and using what they call the turn-off technique, so you draw the main sequence and look at what mass stars are departing from the main sequence, you can sort of estimate the typical mass for stars in that cluster, and presumably the supernova progenitor was as massive as that or more, and they found for this particular star a high mass of maybe 30 solar mass. Now we run into a problem. If you use the common techniques to estimate the ejecta mass of this star, you find that the ejecta mass was small, maybe 5 solar masses. However, these authors claim that not only the initial mass was large, but also probably if it evolved to a Wolf-Rayet star, it still should have been more massive than 5 solar mass, for sure. And here I wanted to make an important point that you should bear in mind when you read the literature. Quite often people translate low ejecta mass to low pre-explosion mass of the star. And this is based on the assumption that successful supernova explosions are always coming from explosions that created a neutron star. So the mass in the remnant is small. It's maybe 1.4 solar mass or so. So compared to the ejecta mass, this is a small fraction. So if you have ejecta mass of 5, then the progenitor, when it exploded, was 6.5 or something like that. I think we have evidence that some explosions that create a black hole can also create a successful supernova. And if you put a black hole remnant, then it can have very large mass. So in principle, you can have a 25 solar mass star explode, have 5 solar mass in the ejecta, and 20 solar mass go into a 20 solar mass black hole, which we know exists. So there are some theoretical arguments that say it's hard to make a supernova when you make a black hole, but there are some observational arguments that say that at least in some cases, you must make a black hole when you make a supernova. So I think this translation between ejecta mass and pre-explosion mass of the star should be taken very carefully. And in particular, many people interpret this low ejecta mass that they get to saying that all of these stars explode when pre-explosion masses are small, and therefore they must be in binary systems because this is the way you can make low mass stars stripped and explode them as type 1bc supernovae. And I think this is a strong claim that is based on an uncertain assumption, which is that the remnants are always neutron stars.
It's the case that all supernovae associated with GRBs are 1C, right?
Right.
And so if it's a GRB doing a rigorous,
There's a black hole. This is one case. And the previous case I showed you before that I think, you remember this type 2n supernova progenitor I showed you? It was 10 to the 6 solar luminosity. That progenitor star must have been at least 50, if not 100 solar masses. And for this particular supernova, we have observations of the evolution, and the ejecta didn't have 50 solar mass of ejecta because they very rapidly declined. So if it takes a little time to diffuse the energy from the ejecta, it must have a low mass. So in that case, there must have been a massive black hole produced, and still the supernova was successful. So I think there's the cumulative evidence is that some black hole forming supernovae exist. And if some of them exist, then there's no physical barrier from them happening also in other classes. Okay. Another point I wanted to make about the size of type 1c supernova progenitors, and here we have, again, mixed evidence. So there are a few events, typically with these extended light curves that rise over a long period of time, that initially show this bump, right? So they rise to a small maximum, and then they rise to the main maximum. And usually we interpret this as evidence for shock, what we call shock cooling. So there was a shock breakout, and then the ejecta are cooling. As we said, if they are cooling over a few days, they cannot have been, the star cannot have been very compact. So these events probably come from either stars with extended envelopes or stars with nearby CSM that creates an effective envelope around the star, even though they are stripped stars. They don't have hydrogen and helium. But in some other cases, we have very good observations of the rising part of the supernovae and very strong tight limits on the fact that there are no bumps initially. And this is from a paper by Corsi et al. And this means that at least for those events, the progenitor must have been really compact. It cannot have had this circumstellar material or extended envelopes. So events of both types exist within this group of type 1c supernova. Yes? R process elements? No. In no regular supernova I'm aware of, there is spectroscopic evidence for R process elements. None. Now, if you look at the relative fraction of R process elements from all heavy elements that are manufactured in supernova, which are, supernovae make a lot of oxygen and magnesium and iron. Compared to iron and oxygen, the fraction of R process elements must be tiny. So even if they make them, it's not unreasonable that we would never observe them. But I don't know of any claims like that. Maybe to give context to the question, right? So in principle, to make R process elements, you need neutron-rich material. So in principle, if you are somehow managing to eject in a core collapse supernova material from close to the core, which is neutron-rich, that material could in principle make R process elements. This is whether it happens in nature is a big question. I don't think it's known at all. Okay, I don't have much more time, so I will tell you a little bit more. One thing is about superluminous supernovae. So we discussed superluminous supernovae, and of course there's a big argument about the mechanisms that provide the energy for these explosions. In my point of view, regardless of what you assume, even if you put a strong magnetar inside that gives most of the energy and most of the luminosity, at least for the supernovae that take a very long time to rise and to decline, you still need a huge envelope to process all of that energy. So the fact that it takes, in some cases, 100 days to rise and hundreds of days to decline means that you must have a massive envelope around the engine, whatever it is. It could be a massive star, it could be a magnetar, it could be whatever. So at least, I don't know, at least 30 solar masses of oxygen and more mass in other elements. So this must be extremely massive stars, more massive than all the progenitors we've so far discussed. And they are, at least the massive ones probably are drawn from the population of the most massive stars there are. So initial masses of 100 solar masses and above. Unfortunately, because these events are very rare, we have so far 0 cases where we actually observe the progenitor star, because none of them happened really nearby to us. Eventually, maybe it will happen, and then we will know more, but this eventually might take, I don't know, decades, so I don't know. We might want to think about a smarter way to estimate the mass. The plot I put here is from a paper by Yerkstrand. This is a spectrum taken in the nebular phase. So I remind you, nebular spectroscopy, the ejecta is mostly transparent. So you are seeing all of the emission that is coming from the ejecta. And if you integrate the emission from all of the different components and all the different elements, you should be able to measure directly the mass. And the comparison here is between the observation in red and one model in blue, which does, I don't know, a reasonable a reasonable job in describing the observation, and this requires 30 solar masses of what they call carbon-burning ashes, which are mostly oxygen and some other heavy elements. It's not a perfect model, but it's a sort of ballpark, and in this paper they review a large number of models, and more, in my opinion, all of them more or less point towards high mass of at least of oxygen. Let me say a few more things about early supernova studies, because I think of all of the methods we discussed so far, this is the one that has the potential to bring the most progress in the next few years. And this is because surveys like ZTF and eventually LSST and Ultrasat that we discussed will find supernovae very, very early on, very shortly after observation. So many people could observe these events after they explode and accumulate this data and interpret it. So what I wanted to show you is two things. First of all, that if you measure the rising light curves of type 2 supernovae or supernovae that come from supergiants, you can get very nice estimates of the radii of these supergiants, especially if you also have UV observations. And this is from a recent paper by Adam Rubin and myself, where you see here the errors, the fractional errors on the radius as a combination, as a function of the combination of observations you have. You can see that the errors shrink once you go here and have UV data. And if you really have nice UV data, you can actually estimate also the extinction. So you neutralize your main uncertainty in such observations. You measure how much dust there is on the line of sight. From the first few analysis or papers about using these methods, we see quite puzzling results. And this particular, for example, is analysis of data from the Kepler mission. So you see this very nice rising light curve. And to fit that, you either have to have a compact blue supergiant progenitor for this supernova, which was a type 2P supernova. So as I explained, this maybe is possible, but it's certainly not what I expected. So it's certainly not true for most type 2P, so it's surprising. And if we keep getting this answer for more events, then there's certainly some contradiction here. Or else you can say that there's some circumstellar material around the supernova, and if you add circumstellar material, you can have a sharper rise. And then, of course, it's a more complex system, and it will be more difficult to get progenitor information out of it. And I showed you examples for that, right? If you take a spectrum early on, you can measure the properties of the circumstellar material around the star, and that gives you information about the composition of the star before it exploded. And of course, this is also very interesting. Oh, yes?
Would circumstellar material be expected for like red supergiants?
Yeah, excellent question. So from the simplest stellar evolution model, no. But there are many variants on stellar evolution that do predict instabilities in the late phases of massive star evolution that could drive, in principle, sort of mass loss that could explain this circumstellar, especially since this circumstellar material seems to be confined to the close vicinity of the progenitor, which means that it was not emitted a long time ago from the progenitor because it didn't have enough time to move far away. So we're talking about instabilities that might happen in the stars, I don't know, a few months, a year before it explodes. And I think this range of timing is certainly not well understood in stellar evolution models, or it's not fully solved at all. There are many complications that could explain at least this.
How would you know it should be confined?
We have observations later on of these supernovae, and we don't see any signatures of circumstellar interaction. So we see circumstellar interaction early on and then nothing. So there must be some CSM, and it must be located close to the supernova, but not far away. Two. So one of them is consistent with the red supergiant, and the other one is not. And so, unfortunately, Kepler is about to shut down. It's now in its final campaign. During this campaign, we might get a few more supernovae like that, because this campaign is actually designed to find more supernovae. And then that's it. That's going to be it from Kepler. But we can get similar data from ZTF and later on from Ultrasat. So the techniques should still be quite useful. And now the final slide I wanted to show you. I have two slides. about systematic studies, and I will go through that briefly because I want to keep some more time for questions. So in principle, let's say you don't, you give up on your hope to find the progenitor of this particular supernova, but you want to analyze a sample of supernovae and know some statistical inference about the population of progenitors. There are many ways to do it, and I show you a few of them. Here is a cumulative distribution of the metallicity you measure at the location of different supernovae. So here in particular, it's the oxygen abundance. So here you have events with low metallicity and with high metallicity. This is a cumulative plot. And the main thing you can do here is compare different types of supernovae. The blue one, the black one is the most numerous one. So these are type 2 supernovae. And you see that there seem to be some subclasses who tend to be in lower metallicity areas. In particular, these magenta ones are the broadline 1C supernovae that are associated also with GRBs. And we know GRBs tend to prefer low metallicity galaxies, so this is sort of consistent. And there are events that seem to have to lack this low metallicity tail, so to be concentrated more on high metallicity regions, in particular types 1B and 1C. So this could tell you that the progenitors of these classes come from intrinsically more metal-rich stars. This makes sense because more metal-rich stars have metal-rich atmospheres and they have stronger winds. So they can lose more mass, they become more stripped, and then they would tend to become type 1b and 1c supernovae that have no hydrogen, rather than type 2 supernovae that retained some hydrogen and didn't lose it in the wind. This is a different type of analysis from Mond et al., where they look at the neighbors of the massive stars. Remember we said that massive stars like to live in groups or clusters of massive stars. And in this case, Mond looked at the locations of known supernovae of different types and analyzed the population around the supernova to see what is the typical age of that population. And he finds younger ages, so higher masses for type 1Cs, and lower or somewhat lower, 1Bs and 1Cs may be the same, but lower ages for type 2b supernovae, which are these orange ones. So maybe there is a mass sequence here, like less massive, more massive. Okay, this is this sort of analysis. You see that the signal is not very strong, so it's hard to make a lot of progress. This is from a paper by Arkavi et al., who looked at the distribution of host galaxy luminosity as a function of supernova type. Now, the more massive galaxies tend to be more metal-rich because there were more metal sources like supernovae in that galaxies, and also because of the deep potential well, they retain all of these metals in the galaxy, while dwarf galaxies with low masses tend to be more metal poor. So if you use this correlation, which is quite strong, as an indication to the metallicity of the galaxy, and because of that, presumably also to the metallicity of the supernova progenitor, note that there is quite a bit of jumping around here. You can get interesting results. And in particular, what Yair showed here, and then Steve Schultz, who's here, is actually now working on a much more systematic and larger reanalysis of this data, is that the fraction of type 1C supernovae, regular type 1C supernova, goes down as a function of metallicity. So as before, type 1C supernova seem to prefer more metal-rich environment. Broadline type 1C, the GRB supernova, prefer metal-poor galaxies. And here you can see that 1Bs go down and 2Bs go up as a function of metallicity. So it seems like the star doesn't know if it's going to be a 1B or a 2B and decides on that based on metallicity. So if it's a bit more metal-rich, it will lose a little bit more mass, and then it will become a 1B. And it will lose a little bit less mass, it will become a 2B. So there seems to be some sort of a metallicity effect here. Of course, you can argue whether all of this is statistically significant, and maybe we should wait for Steve's paper to know this, the final answer. In particular, by the way, this is very intriguing. So it seems like type 1C broadline supernovae like lower metallicity except for the last beam. So maybe they don't like very low metallicity. But of course, this could be a fluke. Okay. In my supernova chapter in the Supernova Handbook, there's a summary of everything I said so far, more or less. So each class of supernova, what we think is the physical origin, what is the evidence that we have for that, and some references. So if you want to see more, then you can go and look at this chapter. Thank you very much.
don't know of any type 2 supernova progenitors which are more massive than, say, 15 solar masses. Not the 30 solar masses that you see in the galaxy. Whereas we definitely know of type 1 supernovae that are like 30 solar masses, 40 solar masses.
Yes.
So what aspect, like what is the difference between these red supergiants and these type 1 supernovae that causes these to collapse to black holes so that these produce supernovae?
Yeah, it's a good question. I don't know. Well, in principle, if you recall the previous lectures, there's some aspect that theorists like. Observers have no idea about this because it's not something we can measure, which they call the compactness of the core. So the density structure of the center of the star is not necessarily always the same. And if a lot of mass is concentrated in the small center of the core compared to some other star that might have a similar mass of the core but distributed over a larger distance, it will be easier to explode the less concentrated core than the more concentrated core because you have less of a energy barrier. And then maybe this goes to a neutron star, this goes to a black hole, or this manages to explode and this doesn't. So maybe it would differ between different progenitors, but I don't know of a reason to think why supermassive stars would have more concentrated cores than stripped stars. So the bottom line, I don't know the answer for that. I don't think the answer is known. And it's a very good question.
I have a question about these type 1A CSS models. Observational data. They show a lot of Gaussian marks, and what are those Gaussian from?
Right. So what I think is that if you look at gas in our galaxy, the strongest lines in absorption that you see in any gas clouds typically are sodium and calcium. This is not because sodium and calcium are common elements, but because these particular lines of these elements are very, very strong. So the chance for a photon to be absorbed in this line is larger than any other element. And I think the same goes here. It's not that the ejecta or the CSM is very rich in calcium. It's just, you might think like solar metallicity or something, but you see strong calcium lines because these are just strong lines. Yes, I don't know that there is a model that says that these are calcium rich compared to other things.
So if you compare the supernova with progenitor detection with those we don't have, so do they look the same as what we say? And also do you expect the progenitor even have some evolution in redshift?
Yeah, it's a nice question, and I'm not sure I don't think I know the answer. So the question is, let's say that we take the sample of type 2 supernovae, let's say, in nearby galaxies. Some of them we have progenitor detections, and some of them we don't, and compare. And I don't know if somebody did this. So I don't know the answer to that. It's a nice idea.
So could you go back to the metallicity environment plot?
Yes. This one or that one?
That one.
Yes.
So it looks like one of the largest differences on this plot is between type 1C broadline and type 1C not broadline.
Yes.
And so this seems like they're two very different classes.
Yes.
So I was wondering whether spectroscopically there's anything in between, or is it sort of just like...
There are events in between, yes. But I also agree that they seem to be physically, they come from different progenitors. Now, remember, what we are seeing here are exploding CO cores. Now, many channels would lead to an exploding CO core. So the spectroscopic appearance in that way is a bit of a coarse. So it tells us what is the composition of the outer ejecta. It could have, for example, let's say a very different engine, right? Maybe some of them are like accreting black holes, and some of them are neutron stars. But if you are seeing all of this through 5 solar mass of carbon, oxygen, ashes, they will look quite similar. Maybe one of them will have more ejecta per unit mass, so it will have broader lines, but that's it. Yeah. But I think in terms of progenitors, they are quite distinct. And still there are intermediate objects between them. And we can argue whether they belong to one class or not, or maybe there's really a continuum. Yeah. The statistics is not large enough to say if they're like bimodal or... It's an interesting question.
You had a comment about blue supergiants
Yes.
in type 2P.
Yes.
Could you put back the plot that made you say that? Because
Right.
it sounds really strange.
Right. I was wondering why you're not stopping me while I was talking and saying this. Yeah. this is not surprising.
Which part?
That you are polite. Here.
Yeah.
So, so these are several events that are similar to 87A. In
Lines or 87A?
the lines are 87A, yes. So you see, for example, this one is flat for 50 days, and then it has this big nickel bump, like you have in 87A.
Oh, yeah.
Yes.
That's fine. I like it too.
Right, so let's say this one. So this one initially is flat, and then it has this big bump, which is similar to 87A, and we understand theoretically that it comes from nickel, contribution from nickel. And here we have something a little bit different. Here it is actually even going down and then coming up to 87A. But it's much more luminous at the beginning than 87A used to be. And still, eventually, it behaves the same. And also, spectroscopically, these events are similar. They happen in similar galaxies. So I was wondering, at least these papers and also previous papers about these objects all say, okay, these come from blue supergiants. But it seems like if these come from blue supergiants, then some of them are able to sustain a plateau, maybe a shorter plateau, or maybe only initially. And if they don't come from blue supergiants, then
But they're spectroscopically like a 2P?
yes.
That's,
Yes.
I mean, it's based on the
Yes,
That's
yes.
why I said-
Spectroscopically, they are very similar to regular 2Ps, and the light curves are similar to 87A with some range of behaviors.
So it's really the fact that it doesn't rise that much. So the supernovae on the left, whoever that is,
On the left, yes, 2004 EK, yes.
you're saying it's because it doesn't show the same rise as 87A?
Well, I'm just saying that it seems like, you know, up to less than half a magnitude, it's on a plateau for 100 days. Right? It goes a little bit down, a little bit up, but it is able to sustain the same luminosity for a long time.
And you know it's a blue supergiant now?
I don't know if it's a.
Wait, so that's what I'm trying to understand.
Yeah, I'm saying.
You don't know if it's a blue
I don't know it's a blue supergiant.
So then why are you saying what you said?
Because it's very similar to 87A in all other respects.
No, but I mean, A7A is a blue supergiant.
Yes, that we know.
These other supernovae
Yes,
are just supernovae
yes,
that you're putting on a plot.
yes.
For an A7, but you don't know
They are.
if they were a blue supergiant or a red supergiant. You have no
I-
idea.
No. I don't know,
Okay.
but I do know that of all the supernovae we know, these are the ones that are most similar to 87A.
I see.
Okay. Then you can say, okay, still all of those are red supergiants, and 87A was a blue supergiant, and yeah, maybe that's the case. I wasn't claiming I have a proof that blue supergiants can make type 2 plateaus. I don't.
No, I was just wondering if it can be a combination of shock cooling and a lot of nickel.
Yes.
Like Udi.
Exactly. Right. I think that if in 87A we have a lot of nickel and it's centrally concentrated. If you mix it a little bit outside and put a lot of energy in the shock cooling, then maybe you can create something that looks like a plateau. Maybe it's not going to be exactly flat, depends on the band and so on. Yes. I think it's not impossible to make not a, and these are not luminous. Right? It's not a very luminous plateau. It's not a 10 to the 43 plateau. But 10 to the 42 plateau, can you make without a red supergiant? I don't know of a proof that you can't. Okay, maybe you can. And if you can make it, then you can maybe you can make it with a blue supergiant also.
Be like a blue supergiant with a slightly larger envelope than the
If you know, blue supergiant is 10 to, let's say 10 to the 12, right? If you make it 10 to the, 5 times 10 to the 12, 7 times 10 to the 12, so it's not that different from a red supergiant, right? So, right, yeah. But maybe, yes. So, right. But I was saying this in the context of the fact that observations of the early rise sometimes want something that is not 10 to the 13, but deep in the 10 to the 12 regime. And the question is, can these things still make plateaus? And I think that's an interesting theoretical question to solve.
You showed that a lot of the constraints that we have are like the effective mass.
Yes?
And then you also showed the field of environmental studies, and that some of the studies study the population of those supergiants or
Progenitors, yes.
So how strong is how strongly do we know the stellar evolution from this point to this point? I mean, there be,
Mhm.
how much uncertain is the path from this one to this one?
So a prescription that takes a star of initial mass X and tells you how it's going to explode as a supernova and with what ejecta mass does not exist. That certainly we don't know. But some of these environmental studies are actually not doing that, right? If you're looking at the apparent masses of stars that are left over after the supernova exploded, it's not like measuring their initial masses. You're measuring their current masses. And if their current masses are big, so their initial masses must have been bigger, and the supernova that already exploded must have been even bigger than that. So you're getting a pretty safe lower limit on the mass of the progenitor from the environmental studies. But how to exactly follow the mass of an evolving star depends on many parameters: metallicity, mass, rotation. That's not going into magnetic fields and other stuff. And we discussed, all these convection complications and stuff like that. Yeah.
So again, I'm sorry, how do you get the lower mass boundary?
Let's say a supernova exploded. I'm looking at what stars survived near the progenitor. Presumably they were all formed at the same time. The supernova progenitor exploded and this one didn't explode. And I can ask, what is their mass now? This is the mass after they already lost some mass because of the time that passed. And I can estimate the current mass. And then, and I presume that since the supernova progenitor already exploded, it must have been at a higher mass because the lifetime of the star goes down with its mass. Right? So a more massive star is shorter lived than a less massive star. So the first star to explode is going to be the most massive one. So if the supernova exploded, everything else should be lower mass. And the mass I measure now is lower than the initial mass. So if I measure 20 now, then the initial mass must have been more than 20, and the supernova progenitor mass must have been even more than that. So the 20 is really a lower bound. In the best case, it's 20, and it could be even higher.
And how dispersive like the masses?
How do I measure the mass of the existing stars?
No, like you get a variety of masses, or are they all in a very bound mass
No.
range?
No, there is a variety of masses, and I take the highest masses among these stars to be the limit on the supernova mass.
Is that the last question over there?
You mentioned that sum to n from environmental studies need to be from lower mass
Yes.
progenitors.
Yes.
This is just because they're in environments where there wouldn't be any massive stars, or because they're further away?
They are far away. If a star is in a galaxy and it's not sitting inside a star-forming region, you can still say, well, it might have been born in a star-forming region, and since then it traveled because it was kicked out due to interactions or to the companion having gone supernova or dynamical interaction in the cluster. And then you can say, okay, how far away could it travel? And that depends on its lifetime. Now, if it's a very low-mass star, it could travel the entire galaxy, like low-mass stars do. But if it's a massive star, it cannot go very, very far. So the more massive it is, the more closely correlated it should be with the localization of star formation centers, let's say. Or
Is this a bigger effect than what's observed for LBVs? Isolated?
That question requires the definition of LBV, and that is a bloody war between the two leading LBV experts, Humphreys and Smith, which I don't want to be a part of that war. And anyway, even if I wanted to, I have no idea who is, I don't know the answer to that. So one of them says yes and one of them says no.